Okay, hello everyone, and welcome back. So we're going to be continuing our discussion on lazy methods for classification regression, in particular nearest neighbor methods. Um, the topic for today, or at least the first topic, is what I'm generally referring to as reduced nearest neighbor. But before I get into that, I want to see if there are any questions from last time or anything leading up to now. All right, well, we'll get started then. And of course, if you do have questions, as always, feel free to just put them in the chat window. So this topic of reduced nearest neighbor, one of the issues that we are going to try to address today is the fact that nearest neighbor search is expensive. Now, when we talk about it being expensive, this is a little bit different than what you might encounter in an algorithms course where one of the common things that differentiates between tractable and intractable is whether or not we have a polynomial time solution versus an exponential inverse time solution. Well, nearest neighbor search is polynomial time. But the problem becomes when you have either or both a very large data set, and these days it is not uncommon to be dealing with data sets in the millions or even more examples, or where the examples are very high dimensionality, where we're talking hundreds or even thousands of dimensions. And so even though searching the space of our data set is polynomial, it's quadratic, what you find is when you're getting to thousands times millions, it still takes an awful long time. Well, there are a couple strategies that we can employ to speed up the nearest neighbor search. One is employing clever data structure. We're actually not going to talk about that specifically in this class, but for those of you who are interested, one of the most famous data structures here is something called a KD tree. And what that does is it actually reduces the search from order dn, where d is the number of dimensions, and n is the number of examples, to order d log n. That's an average time performance. The worst case is still no better. Related to this data structure, in fact, it's a technique that we often use with this data structure, but there are also other clever indexing schemes that accomplish basically the same thing. It's what we call a branch and bound search, where the idea here is that as we are looking for a nearest neighbor, we can use distances to other neighbors to bound how we are searching the remaining space rather than doing a comprehensive search over all of these examples. Again, we're not going to talk so much about branch and bound search here. But the third thing we are, and it has to do with, well, first is feature selection. And we've already addressed this a little bit, both in the previous classes dealing with things like stepwise forward selection or stepwise back elimination. And we even talked last time about how nearest neighbor is sensitive to noise in the feature set. So by doing feature selection, we're reducing the dimensionality of the problem, and that is, of course, reducing one of those terms in that quadratic of complexity. But the other has to do with data set reduction. And, from a machine learning perspective, this may seem a little bit counterintuitive because, for one thing, we're dealing with the person dimensionality, the idea of being there, that more dimensions, you need exponentially more data to learn the concept. And in fact, there's this mantra that we use in machine learning that more data is better. Well, in general, that's true, but what we're going to do is we're going to basically think about nearest neighbor from a geometric perspective, where if we can take advantage of that geometry, we may find that a lot of the examples that we have stored up in our data set really aren't helping us in terms of doing prediction. In which case, why keep them around when all that does is increase the cost to search? So let's throw them away. So what this does is it leads to two methods. The first is called edited nearest neighbor. And the second is called condensed nearest neighbor. And both of these algorithms have the objective of trying to find a subset of your data set that still enables you to do nearest neighbor prediction well. And we're going to begin by looking at the edited nearest neighbor algorithm. And the interesting thing here is that edited nearest neighbor actually comes in two flavors, where the first basically removes, let's see which I'm getting the order right. It removes erroneous examples. And I have to be a little bit careful here. It's not so much that the examples are erroneous, but the examples, by being in the data set, lead to errors because they happen to be near the decision boundary, and yet they're actually not really conducive to finding a class when you're searching in that space. And you'll see what I mean. So the flip side says we're going to remove correct examples. Same thing, it's not so much a matter of are they really correct or not. It has to do more with whether or not they are useful in terms of doing correct classification. And the idea behind this, well, the idea behind the first is if we remove these examples that are causing errors, then you can think of that as removing the noise. Those examples that are noisy in some sense and therefore deceiving the classification. And then what that does is it tends to separate the classes to make the boundaries more distinct. The second one, this idea of removing the correct examples, the idea here is if we are already getting correct classification with these other examples, then these other examples are redundant. And so just take them out because all they're doing is increasing the computation. Now, obviously, or hopefully obviously, we're not going to do both. Because if you do both, you end up with an empty set. All right, and then the condensed, and I'll go through the actual algorithms in a minute. The condensed nearest neighbor algorithm that we're going to look at basically adds examples from our training set, which I guess depending on the day we've been denoting D, sometimes we've been denoting X or X, as needed. Now, what's interesting about these two methods is that if you relate them back to what we were doing with feature selection, then the edited is sort of like stepwise backward elimination, except that here we're eliminating examples instead of eliminating features. And the condensed nearest neighbor is sort of like stepwise forward selection. Except again, we are adding examples rather than adding features. Okay, so I'm going to start getting into the actual algorithms themselves. Before I do that, I'm going to pause to see if there are questions. Okay. So we're going to begin by looking at the edited nearest neighborhoods. Okay. So basically, the edited nearest neighbor algorithm works like this. We're going to consider all of the examples that currently reside in our data set script X. And then for each of these examples, the first thing we do is we classify Xi using the rest of the data. Now, the first thing I want to stress about this particular step is we're not dealing with any of the data in the test set at all. This is purely operating on the training set. So what we've just done is we've pulled out one training example, and then we say, let's use the rest of the training set to classify that example. Now, we already know what the class should be because it's a training example. It's been labeled. But now we're seeing what the rest of the data set tells us it thinks the label is. So from here, we compare the classification return to the stored label, which is exactly what we do normally when we are evaluating classification. We're basically looking to see, did the rest of the data set classify this particular point correctly? So if the classification of X is wrong, mark for deletion. So this current loop is basically going to walk through all of the data, one data point at a time, to determine if the current data set is able to classify it correctly or incorrectly. If it's incorrect, we mark that data point to be removed. After we've gone through all of the data, we go back and repeat this as long as the performance on a validation set does not degrade or until no further points are deleted. Okay, so this is a little bit different than what's been going on with the loop up above, because here we're assuming that we have broken out a separate subset of the data, a validation set. So think of this as being analogous to the tuning set that you were using on the previous assignment. And once we do a pass through that first loop, we're going to take the result as our training set and then evaluate how well we do classification using this independent validation set. Get a measure of performance, we go back and go through that top loop again. This is going to give us a new training set that we then evaluate against the validation set. And we keep doing that as long as performance isn't degrading, because even if it flatlines and it doesn't get any worse, we can continue to delete because it's continuing to enable us to reduce the size of the data set. Now, one of the things to keep in mind here is that this approach can be either incremental or batch. What I mean by that is the way I've written the code now, it's batch, where we are marking all of the points to be deleted, and then when we finish the loop, we go ahead and delete them. In the incremental case, as soon as we've marked a point for deletion, we go ahead and remove it from the data set, so that when we go on to the next point to evaluate, that particular data point is no longer there to assist in the classification. All right, are there any questions? That's the first edited method. Okay, I'm not seeing any. So the second edited nearest neighbor method is really just a slight change to this algorithm. Where basically we take this right here, where we're testing to see if it's wrong, and replace it by testing to see if it's correct. If correct, we mark it for deletion. And again, the rationale here is if the data surrounding that particular point is classifying the point correctly, then we don't need the point. All that does is add to the complexity of the search, so we may as well mark it for deletion. Otherwise, the algorithms are identical. As I said, you don't want to do both, so you choose one or the other. I forget if in the assignment I specified one versus the other. If I did, obviously use that. If I did not, then it's your choice. You do not have to implement both. Are there any questions about edited nearest neighbor? When you say does not degrade the performance, is it if the performance degrades at all or degrades under a set value? What do you mean by a set value? You mean a minimum amount of degradation? I'm not getting an answer. Oh, here we go. In terms of how we are calculating the performance, would that not have a value? You're calculating the performance using some loss measure. If the loss measure does not degrade, then you keep going. As soon as the loss measure degrades, you stop. Does that answer your question? Okay, great, thanks. Any other questions? All right, then let's look at the other method, which is called condensed nearest neighbor. All right. So for this, what we're trying to do is to select the smallest subset, which I'm going to denote with a Z, of our training set, such that using Z in place of X does not degrade performance. In fact, this is exactly the goal that we had with edited nearest neighbor as well. All right. So here's the approach. We initialize Z with some random choice from X, just to get it started. And actually, there are some versions of this algorithm that say you start with a Z being the empty set. It turns out that in reality it's no different, which you'll see in a minute. But here we're starting it with an example, which, as you'll see with the code that I present in a minute, guaranteed that that example would be added to our subset Z. And then we repeat the following. So for all X in our training set in random order. All right, let me pause for a second. I'm not going to add all of the nitty-gritty details that you would have to do to code this up correctly, but one of the things to stress is I've already added that random X into Z. Think that you're going to have to remove it from X, otherwise you're going to end up looking at it again in this interlude. So we're assuming that we have taken whatever has been added into Z out of that candidate training set. Okay, and then for this loop, we're going to find some point that currently resides in Z, such that the distance from X to that point is equal to the minimum over all examples in Z. In other words, we're finding the nearest neighbor. By the way, both in the edited nearest neighbor case and the condensed nearest neighbor case, the assumption is that we are doing one nearest neighbor. Could you modify it to do K nearest neighbor? I guess technically the answer is yes. But for your implementation within your programming assignment, the assumption is that you're doing one nearest neighbor. All right, so we're finding the nearest neighbor in Z, and now we're going to test if the class of X does not match the class for X prime, add X to Z. So again, if it did get classified correctly, the idea is we don't need it, because in that space we already know how to classify the data. But here, if we're pulling in an example that mismatches, and there could be a number of reasons for that, maybe because we're selecting these at random, we've picked a point a long distance away, especially starting out where the data is sparse. And so we need to sample that space, and so with an incorrect classification, we get You keep doing that until Z does not change. All right, that's condensed nearest neighbor. So again, comparing condensed back to edited, you'll notice that in both versions of the edited case, we start with the entire data set and we gradually reduce it. In the condensed case, if we're focusing on Z, we start with what amounts to the empty set or to a single example, and we gradually grow it. Now, I was going to comment about how we can show that if we had started with the empty set, this still works. The idea here, if Z is empty, when we go to find the nearest neighbor, since there's nothing in there, we default, think of throwing an exception, that therefore we're not getting a correct classification. And then we add it in. So are there any questions about condensed nearest neighbor? So with condensed nearest neighbor, we are not testing the performance each time like when we are developing edited. That's correct. We are not using a separate validation set. Could you? You have to be really careful there, because with the separate data set, you may actually determine, you may decide to terminate too soon. And that's because you're going from a very small sample to a larger one, where in the edited case, you're starting with a large sample, so presumably it better reflects the underlying distribution. When we create Z, we're done. When you stop adding to Z, you're done, and then Z becomes your training set. Does that answer your question? Cool. Any other questions? Separate question on edited. How does the validation set and edited nearest neighbor relate to our entire data set? Will we be using the tuning subset? Yeah, you would probably use something like the tuning subset for that. And actually, this brings up a good point. There are going to be a number of terms that we use rather sloppily. Probably the most consistent term that we use is training set. But even when we talk about a test set versus a validation set versus a tuning set, depending on who you're talking to or what you're reading, some of these terms can be flipped around. Because, for example, remember, we also have this thing that we've sometimes referred to as a holdout set. Well, some people say that the holdout set is the test set. Some people say the holdout set is the validation set. Usually, tuning set is tuning set. You're using that to tune the hyperparameters. And so this is where we have this kind of three-way confusion. And the way I have been using the terminology, just so that we're clear, is that the test set is ultimately what you are using to evaluate generalization at the end. And validation is an intermediate test data set that you are using to do things like the editing or condensing, well, not condensing, but the editing process, or preventing overfitting in some cases, which we'll see with both decision trees and neural nets. But for some, those terms are reversed. So I just want to make sure that you folks understand how I'm using the terms. Are there any questions? So a validation set might be generated from the whole data set as opposed to one of the 10 folds. not quite sure how to answer that. A validation set is a separate, independent subset of the entire data set that you're working with. And you may recall when we were talking about tuning earlier, I even suggested that in an ideal world, you're going to do cross-validation to do tuning as well, as opposed to what I'm having you do, which is a simplified version. In fact, when it comes to actually deploy a model, you're not going to do cross-validation to evaluate the model by itself, because you only want one model, you don't want 10. In that case, you'll do cross-validation only to tune the hyperparameters. And then once you've got those hyperparameters, you can go back and you can train your model on basically the entire data set so that you can then deploy it using as much data as possible. The process I have you using for these projects is more of a process that's used for experimental evaluation of different model choices so that you can then figure out which direction you want to go. Now, I don't know if that just made it harder, more confusing, or if it cleared it up. So let me pause to see if that generated any other questions. Okay, great. Anything else on edited or condensed nearest neighbor? If not, we have one other major topic to talk about before we move into, well, we actually have 3 topics to talk about before you're ready to do everything for your project. And before you can do the quiz tomorrow, on Friday. All right, so let's move on.
New page.
Up until now, we have only been discussing the nearest neighbor methods with respect to classification. And the lead into that was this whole discussion on density estimation, which we looked at Bayes' rule and showed how we were estimating the priors and the likelihood terms from Bayes' rule. And that was also kind of done with from the perspective of doing classification. But I'm also asking you to apply nearest neighbor for solving regression problems. So we need to talk about that for a little bit. This is going to look very similar to what we did when we were building up the techniques for density estimation, except in this time, instead of estimating a density, we're estimating a function of some kind. All right, so to make this a little bit more formal, in regression, we have our data set X, oops, hold on. Where, again, the vector X you can think of as being, oh wow, that just messed that up. I'm sorry. So the vector X is our feature vector, just like we had in classification. And then R, we refer to it as response variable, and it's going to be taken from the set of real numbers instead of being a categorical value that corresponds to a class. So it's essentially the same as classification, except that we're in a real valued space instead of a categorical space. And then we typically assume that the function or the response that we're trying to find is based on some function of x plus a noise term epsilon, where that noise term is usually drawn from a normal distribution. Well, I've made it a standard normal. You could make it non-standard by having a non-unit, I suppose. For linear regression, we typically assume that that function x, g of x, has this form. Which you've sort of seen before. I mean, if all you do is look at this part here, that's the same as what you had in Winnow. Now, what we've done is we've added this extra term W0, which effectively what that does is it allows the linear function to have a different intercept. So we're not requiring the function to go through the origin. All right. But one of the nice things is that non-parametric regression does not assume linearity. So in fact, the method that we're looking at here is much more general. And as you'll see, it can actually pretty much represent any type of function that you need. All right, so to do this, what we need is the concept of a regressogram, which is directly analogous to the histogram that we were talking about when doing density estimation. Okay. So in particular, if we look at just a naive regressive or a simple regressogram, what we're going to do is we are going to define our function g based on some query point, which will denote x sub q. And we're going to calculate it this way. Oops. Now, that looks more complicated, perhaps, than what we saw with the density estimation. So here, we can take a closer look at that b function. We're going to define b of xq compared to xt as returning either 1 or 0 if xq is in the bin of xt, 0 otherwise. So what did we just do? There is an assumption here that we have chopped up the data into bins, just like we did with the histogram estimator. And for this particular version, we start bins at some origin x0, just like we did before. When we do that, this is what the regressigram looks like. Now, up at the top, you see an example where we set the bin width for our regressigram to be 6, which is a little bit weird because we only have 8 values on the x-axis. But since our origin is 0, that means the first bin has width 6, and then the second bin only has width 2. You could, I suppose, imagine this being extended out, possibly to include values all the way out to 12. And then, for any query point that falls in one of those bins, so take the left-hand bin that goes to 6, doesn't matter where it falls, you're going to take all of the data points that happen to fall within that bin and basically just calculate the average. In the middle, we see it where the bin is a little bit finer, the bin size is finer, where now we have a bin width of 3, and down at the bottom, a bin width of 1. Now, the one thing you can notice from the regressigram is it doesn't look very smooth. And remember when we were doing density estimation, we had exactly the same problem, that it wasn't very smooth. So what we would like to be able to do is consider some strategies that perhaps could smooth this out. One idea that could be applied is to say, okay, I'm going to assume that the data within a bin happens to follow a linear model. And I've got all of the machinery from doing linear regression, which we actually don't cover at this point in the class. But if we did, and we fit a linear model inside each of those bins, now the regressigram looks like this. They're no longer step functions, except a couple places. And we actually see some variation where, but they're all linear inside. I mean, I think one of the, well, the bottom one with h equal 1 I find particularly interesting. And what this is also showing is if you only have a single data point within a bin, you have no choice but to return the value of that data point. All right, so that is the simple regressigram. Well, sorry if I missed something, but why is B crossed out? It wasn't crossed out, that was noise. That was just noise from the Bluetooth receiving the signal from the marker. So don't cross it out. So you recall that the first thing that we did to try to smooth things out with the histogram, and where we created our naive estimator, was to say we're not going to assume an origin, but instead we're going to do a local estimate based on the query point itself. All right, when we do that, we get what's called a running mean smoother. And mathematically, our estimator looks like this. You'll see it's very similar. All right, so this is very similar to what we saw with the naive estimator for density estimation, where here that W function is again simply 1 or 0 based on whether or not point falls inside the bin. And when we apply this, this is what we get. Now for h equals 6, it doesn't look like it has done a whole lot of good for us. But look down at h equal 1, we're still dealing with those step functions. But if you compare it back to this, you can see that we are starting to smooth things out. There have also been methods applied where, again, since you're capturing a bin local to the query point, you can fit a local model there as well. And the interesting thing when you do that is as you move the query point through the space, since the bin is moving with it, that would also actually tend to smooth out the estimate. And then this actually suggests the last method that we're going to look at here, which basically is applying what we call kernel smoother. Which again is very similar. Okay, hold on. Which is very similar to, boy, it doesn't want to do that, does it? To the kernel density estimator that we saw earlier in the unit, where now we simply replace this with a kernel function, and it is common for that kernel function to follow a Gaussian, something like make sure everything's right in here. It's okay. Something like that. Now, this particular version does not include the full multivariate joint where you've got the covariance matrix to deal with. If you want, you can replace it with that version too. And then just substituting back into the smoother we have at the top of this gives us our kernel smoother, which looks like this. And as you see, now it is much smoother. Okay, that's all I had planned for today. So the plan for Friday is to talk a little bit about clustering, since you also have to implement a couple clustering algorithms for your project. But with the minute I have left, are there any questions? All right, well, thank you all. Again, I'll post the recording as soon as it is available, as well as the whiteboard notes and the slides. Otherwise, I will see you on Friday.